Bismillahirrahmanirrahim. This video is to explain the inverse Laplace transform. Laplace transform converts a function defined in the time domain into a function defined in the frequency domain. The inverse Laplace transform performs a reversed operation. We would have a function defined in the frequency domain, and the inverse Laplace transform will convert it into a function defined in the time domain. The idea of the Laplace transform as well as the inverse Laplace transform comes from the mathematical rule which applies to any equation. An equation is two balanced sides separated by an equal sign. Like the equation define the voltage on the coil. V equals L di by dt. So mathematically, any operation will be done to one of the sides of the equation must be performed on the other side. Let us try to solve the equation for the current. To do so, we will have to divide both sides by L, or multiplying by 1 over L. This will give us V over L equals di by dt. This equation mathematically is 100% equivalent to this equation. After that, to find the current, we will multiply both sides again by dt, and then take the integration for both sides, which gives us I equals 1 over L multiplied by the integration of Vt dt from 0 to t. This equation, again, is the same as this one, which both of them are the same as this one. Because for every operation we have performed, we performed similar operations on both sides. This is very similar to what happened or what happens when applying or performing Laplace transform. Let's say we have a function f of t equals cosine omega t. Multiplying both sides by eos minus x st, we will have eos minus st multiplied by f of t equals eos minus st multiplied by cosine omega t. Again, we multiplied both sides with eos minus st. This equation is 100% equivalent to this equation mathematically. Like we did here. After we take the integration, we define the left-hand side as the current as a function of time, I of t. The same here. After we multiply it by es minus st, we will take the integration of both sides and we will call the left-hand side as the Laplace transform of f of t. This left-hand side would then equal the integration from 0 to infinity of the right-hand side, eos minus st cosine omega t dt. So we apply the same operations. So this equation is 100% equivalent to this operation. We started by multiplying by eos minus st, and then we took the integration for both sides. As we expect, or as we should expect, the inverse Laplace transform should be the reversal of these operations. We started here with f of t, we finished with f of s. Here we will start with f of s. We multiplied here with eos minus st, which is like a division with 1 over eos st, because the negative exponent means denominator. We can read this as 1 over eos minus st, or 1 over eos st. So the first step here is to multiply, not to divide, but to multiply both sides by eos st. So we want to multiply f of s by eos st, and then we'll take the integration. And we must notice that the multiplication by the exponential function defines the variable which we need to have at the end. In the Laplace transform, we need a function of frequency, function in the frequency domain. So by multiplying both sides by EOS minus ST, we defined or we entered in the equation the frequency. By integrating with respect to time, and by the definition of the integration limit from 0 to infinity, would ensure, or we will ensure, that the time will disappear, the time as a variable will disappear from the results, and the function in the left-hand side will be defined only for the frequency, again, which was entered using the exponential multiplication. Again, in the inverse, we multiply by e is positive st, allows us to enter the time as a variable. Then by integration, and we will, with integration with respect to frequency, here I forgot to type ds, I'm sorry. Then we will eliminate or get rid of the frequency, and the time would be the variable to be left. Uh, and this is reached by defining the integration limit from sigma minus j infinity to sigma plus j infinity. I'm sorry, this is positive, and by multiplying by 1 over 2 pi j, which will allow us to get rid of the imaginary components, allowing us to have a function in the time domain with only real components. This is important in the electrical engineering, for example, because we are dealing with quantities like voltage and current, which are real or real physical quantities. So in summary, if we have a function f of t, using the Laplace transform, we can have an equivalent function for f of t in the frequency domain, which is f of s, and this is defined as the Laplace transform, or f of t, which equals to the integration with respect to time from 0 to infinity of EOS minus ST multiplied by f of t. If we have a function f of s defined in the frequency domain, we can find its equivalent in the time domain using the inverse Laplace transform, defined as L minus 1, or inverse Laplace transform of f of s, which equals to f of t, which equals to 1 over 2 pi j for the integration, multiplied by the integration from sigma minus j infinity to sigma plus j infinity of f of s multiplied by e os st ds. The performing of the integration can be overwhelming. There are tables defines the pairs between f of t and f of s. So to find the inverse Laplace transform for any function f of t, the first step is to, or the first strategy ever, is to check the table. For example, if we have f of s equals 1 over s plus a, check the table first. If it is there, you will find the f of t listed in the table. 1 over s plus a, this is a unit step function defined in the frequency domain with a shift in the frequency. So you can see in the table that it's defined as EOS minus AT. It's actually multiplied by unit step function. Unit step function equals 1 from 0 to infinity, and the Laplace transform is defined from 0 to infinity. So unit step function can be replaced by 1. So it is in the table, you will find it as EOS minus AT. So first step to find an inverse Laplace transform is first to check the table. If you cannot find the inverse or the pair between f of s and f of t in the table directly, then we will use some manipulations. I would find here 3 strategies, very straightforward strategies. first of them. Let's say we have f of s equals 12 divided by s squared plus 4s plus 13. If you check the table, you can find that there is an entry in the frequency column defined as omega divided by s plus a squared plus omega squared. So if you have a function in the table which is similar to the f of s you have, then you need to manipulate it if you can to have it similar to the exactly to the one in the table and then find f of t. We can do this here. We can define the s squared plus 4s plus 13 as 12 by s squared plus 4s plus 4 plus 9. Then the s squared plus 4s plus 4 becomes a complete square. We can define it as s plus 2 squared plus 9. This is exactly the same as omega plus divided by s plus a squared plus omega squared if we uh, decompose the 12 into 4 by 3. The 4 can be extracted. Then we'll have numerator as 3, denominator as s plus 2 squared plus 3 squared. 9 is 3 squared. This is exactly the same as this. If you check the table, you will find this. You will find that the inverse Laplace transform to omega divided by s plus a squared plus omega squared equals to es minus at sine omega t. Here omega is 3, a is minus 2, or a is 2. So the inverse Laplace transform to 12 by s squared plus 4s plus 13 is 4 eos minus 2t sine 3t. So the first step, check the table. If it is there exactly as the f of s you have, you found f of t. If not, it can be similar. Just try to manipulate it. It can be more difficult, like the example we have. We have s plus 1 divided by s squared plus 6s plus 45. If we check the table, we can find an entry in the frequency, in the column for the frequency domain, as s plus a divided by s plus a squared plus omega squared. So again, we need to manipulate the denominator to have it similar to the denominator to this equation. We can do this by defining s plus s squared plus 6s plus 45 as plus 9 plus 36. Again, s squared plus 6s plus 9 can be defined as s plus 3 squared, and the 36 is 6 squared. The s plus 1 in the denominator, we need to have it as s plus a. So we can define this as s plus a, s plus 3, I'm sorry, minus 2. 3 minus 2 is equals to 1, plus 1, the same as here. So s plus 2 plus minus s plus 3 minus 2 over s plus 3 squared plus 6 squared, exactly like this expression. So we can divide the denominator over the two terms in the numerator, and we can have this expression defined as s plus 3 divided by s plus 3 squared plus 6 squared minus 2 over 6 plus 3 squared plus 6 squared. Again, to have it as omega squared here, we need to have the numerator as 6. So we will multiply the numerator by 3 and divide by 3. So we have here two terms defined. One of them as this expression. The other term is the expression we found here. So the first term, if you check in the table, it will be eos minus 3t cosine 6t minus 1/3, which is from here, multiplied by eos minus 3t sine 6t. t. So this is the definition or the Laplace transform for the omega, for the cosine omega t. But since there is a shift in the frequency domain, the shift in the frequency domain would be converted into exponential function in the time domain. The same applies here. So these two terms would be from the table defined as these two terms in the time domain, and this would be the inverse Laplace transform for this function. The last strategy for manipulating the f of s to have it similar to the ones in the table is using the partial fractions. This would be used if the denominator is a multiplication of functions defined in brackets, like we have here. We have three brackets or three sets of brackets. One of them defined as s, the other one is s plus 2, the third one is s plus 3. We should take every one and make it a separate denominator for a partial fraction. The degree in the numerator for each one is 1 degree less than the denominator degree. We have here the denominators, all the denominators are of degree 1. The highest exponent is 1. So all the numerators for the three fractions would be 0, means it's a number. If any of the denominator is higher degree, like degree 2, for example, let's say that b over s squared plus 2. This means that the numerator would be of degree 1, which means that we'll have a term with s. So we'll define the numerator as bs plus c, and then this c will be d, and so on. The rule is that the numerator would have a degree which is 1 less the degree of the denominator. So this expression would be equals to a by over s plus b over s plus 2 plus c over s plus 3. These are equal, so we will have a common denominator again in the right hand side, and then the numerator will be like that. We will multiply the a with the other two denominators, b with the other two denominators, and the c with the other two denominators. We will have this new numerator. We will multiply, or we will expand every term to have it in this form: a multiplied by s squared plus 5s plus 6 plus b multiplied by s squared plus 3s plus c multiplied by s squared plus 25. This must be equal to the left hand side here, s squared plus 12 divided by s multiplied by s plus 2 multiplied by s plus 3. Since the denominators are the same, or they are equal, the numerators must be equal. So we have here a term having s squared, so the coefficient of s squared here must equal the coefficient of the s squared term here. This means that a plus b plus c equals 1, because here we have as squared and we have bs squared and we have cs squared. So a plus b plus c equals 1. There is no term having the variable s, so the coefficient of s here must be 0. This means that 5a plus 3b plus 2c equals 0, and there is a constant here, or a number 12. So any term here without s, or s squared, will be equal to 12. This means that 6a equals 12, a equals to 2. Plugging this to the other two equations, we will have c equals 7 and b equals plus 8. Plugging this into the partial fractions, we will have f of s equals to 2 over s minus 8 over s plus 2 plus f7 over s plus 3. This is from the table, are the are the inverse Laplace transforms for the unit step functions with some shifts. So the first term would be 2 multiplied by u of t. This can be found from the table. Minus 8 EOS minus 2t multiplied by u of t, the unit step function. But there is here a shift in the frequency domain. This is converted to exponential function in the time domain. Finally, 7 over s plus 3. This is in the time domain defined as 7 EOS minus 3t u of t. We can replace the u of t's with 1. So the result will be 2 minus 8 EOS minus 2t plus 7 EOS minus 3t. Thank you very much. I hope the video is useful. Thank you again.